All right, fantastic. Well, thank you all for showing up this afternoon. My name is Oda, and I work at NASA's Jet Propulsion Laboratory just up the street from PCC, and I work in the education office. I have a number of JPLers on the line with me today, and we'll be talking to you about various locations at JPL, taking you on a virtual tour, and then also answering your questions. We have some of your questions you submitted ahead of time, and we'll grab those, and we'll also answer questions kind of real time in the chat. So if you see something on the tour that you think, oh, I have a question about that, let us know. Just type in the chat. We've got folks who will either interrupt me or will answer it on the chat for you. So for those of you who started with us a few minutes ago, you heard us talking about the fact that this is our outdoor mall, just kind of a general middle of the laboratory location. If you come on a public tour with us, one of the first places you'll go is our visitor center. And there are a couple of things here. I am not going to tell you like everything about the virtual tour, because the thing is, you can go yourself and explore the virtual tour. And it's found at jpl.nasa.gov/virtual-tour. And don't do it now though, because if there's a bandwidth issue, it'll probably slow you down viewing us if you're trying to view virtual tour on your own at the same time. But one of the first things you'll see is this rocket-looking thing here, and this black and white thing at the top is Explorer 1. It was the first U.S. satellite to go in orbit, and it was, of course, second to Sputnik. The Soviet Union put up Sputnik first, but then we got Explorer 1 right on its tail and doing some interesting science. You can learn more about each of these things if you can click on these when you highlight it. You click on that, it'll take you to a web page with more information. And there's also things like you can hover over things like over here, you see the timeline, history of JPL. So there's all kinds of kind of not really Easter egg sort of things, but kind of Easter eggy. And then back here is actually a flight spare of Explorer 1, which is kind of neat. A flight spare is an exact duplicate of the thing that goes in space, except it didn't fly. So it was spare parts. We use those things for troubleshooting. As I mentioned, the general tour would take you into this room. This is our big auditorium where we have public talks and we have giant spacecraft models. So any of these, you can cruise up next to them and see them more closely. You've got one that is in orbit in Jupiter right now. This is Voyager. If you've heard of Voyager, you can scoot back to Voyager. We have two spacecraft, Voyager 1 and 2, that are currently outside of our solar system in interstellar space. So that's pretty cool. Across the room is one of my favorites. This is the Cassini spacecraft that went to Saturn. And that mission is now over, but we are still analyzing data from it. It's just tremendous knowledge. This was a European probe that hitchhiked with us on Cassini and landed on one of Saturn's moons called Titan. And then back over here, we have this cool looking Earth science mission that is getting ready to be launched, I believe in December. So you can learn lots and lots of stuff about all these. You can click on them, some videos, so on and so forth. There is if you go back out to this room over here, you see where it says Visitor Center. That's actually our little museum. And the thing you should know about JPL is we use robots to explore the solar system. So somewhere in your life, you had to learn probably the planets in order, and that's how our museum is organized. We have, starting with the sun, and then the couple of spacecraft that we had that explored the sun, then Mercury, Venus, Earth, so on and so forth. And in front of each of those is a little spacecraft model, or sometimes they're hanging spacecraft models. It tells you about what we know so far about these planets. Of course, we know a whole lot more than that, than is what it says on these signs. So you can click on it and get to websites that give you more information. There's also these little things that it doesn't tell you what it is, but if you can see where the little hand is pointing here, there's a black cylinder that sticks out from the wall. and there's a little marble on it. And that's the scale size of the planet. So if the sun were this big, then Mercury would be the size of that little marble. It wouldn't be that close to the sun. It would actually be a lot further if we had a complete scale. There's a neat video up here I won't show to you right now, but it's a scale of the solar system. It shows you the difference between size of the planets versus distance between the planets. It's kind of fun. But you can navigate this all on your own. You can find the Mars rovers, a couple of the older Mars rovers here. You can scoot on over to the Earth science and the moon. You can see some of our Mars missions back here. If you get back to asteroids and comets, you'll see some cool stuff. There's this stuff called aerogel. If you want to like see some really freaky stuff, check out aerogel. It's like mostly air. They call it solid smoke. You can keep going. There's another big spacecraft back here. This is the Galileo spacecraft that went to Jupiter a while back, and we learned a whole bunch of cool stuff. But you can go all the way around the museum, check out some of our space telescopes, some of our astronomy research. And when you end up at the very end up here, you will be back where we started. And we kind of end with this thing called the Deep Space Network, which we will talk. Well, I guess we're not going to the mission control, but Deep Space Network is how we communicate with the spacecraft that are out in our solar system. We have these giant antenna dishes. These are 72 meters, and if you think 72 meters, that's like almost the size of like 3/4 of a football field. And there are 3 different places on Earth. One is up in like outside of Barstow. If you've driven to like Vegas, you know where Barstow is. It's kind of middle of nowhere. Outside of Barstow is even more the middle of nowhere. And there's an Army base out there called Fort Irwin. And on that base is Goldstone Tracking Station, which is home of one of these giant dishes and a whole bunch of other small dishes. And then we have another similar facility in Madrid, Spain, and another one in Canberra, Australia. So that's kind of the basics of JPL. What we're going to do today is we're not going to take you to all the stops. We're going to take you to some places that you wouldn't necessarily see on a tour if you were to physically come to JPL. And one of the places that we're going to go is called the Machine Shop. And the Machine Shop is where we build spacecraft parts. And Tagui, you want to take over from here?
Sure. So I don't work in the machine shop. I have just used it a few times as a customer, but I've been at JPL over 36 years. So just by osmosis, I've picked up some history. It's a pretty large place, and it has an entire staff that consists of both technicians and engineers, as well as materials scientists. And they machine anything from entire spacecraft parts to tiny little pieces, and to specifications that are down to 0.000, I don't know how many decimal points. And it's state of the art. And the Cassini spacecraft antenna was machined in this machine shop. The machine shop has been upgraded quite a bit over the last decade, maybe a little more than a decade. They now have a lot more modern machines where they can build one part spacecraft part. So they would start with a block of the material like the way a sculptor would. And then the machine, I think this might be something that might do something like that, the one that you've got the hand on right now, and it would just scoop out, it would remove the parts that are not needed, and you end up with this very complex one-piece system. That's mostly all I know about the machine shop. Maybe more, but I can't think of offhand, but okay. Like I said, it's a state-of-the-art place, and they can, you know, if you need it, they can machine it.
Okay. And speaking of needing it, Erica, I believe you're on with us. You had some parts fabricated there. Is that correct?
Yeah, so like you were saying, it is definitely state of the art, and they do have, you know, people who are doing material science research, manufacturing research. So the parts that I've had made, you know, some of it's with the CNC mill and lathes, but some of it's also newer technology in 3D printing for 3D metal printing. So we actually have a portion of the shop that specializes in 3D metal printing. You know, people who are welding those different types of alloys. And so the JPL shop, you know, handles a lot of those really complex parts or kind of research parts for flight and research projects.
All right, cool.
Erica,
So-
is the, if I may just really quick,
Mhm.
is the additive machining part of that you're thinking of?
Yeah, it's actually, it's hard to see it here, but it's kind of in the back corner. So they have a little bit of a separate shop just because those machines have specific requirements and specific access things for who can actually use them.
Yeah, so a couple different ways to make spacecraft parts. You can take a block of material, block of metal, and subtract, basically take metal away until you have a part. Or you can do like the 3D printing, which is additive. You can start with like nothing and start adding material until you get your part. So we do both of those here. And now we're gonna hop over, once you get your parts built, you gotta put your spacecraft together. So we're gonna hop over to spacecraft assembly. And Takui, actually, you are a clean room specialist, correct?
Yes, I'm JPL's clean room engineer, so subject matter expert on clean rooms.
All right.
Okay, so the spacecraft assembly facility, it has these high bays. They're giant, huge clean rooms. This is the largest clean room by volume at JPL. It is, sorry, I can never remember it by heart, but it is quite large. And I have the dimensions. It's 80 feet wide by 120 feet long. It's 44 feet high. So it's pretty large. And the logos that you see in the background, those are all for spacecraft that were assembled in this building over the years. So we just keep building more of them. This particular building has actually two different high bays in one building, which is a little bit unusual at JPL. But before I go to that, since we're looking at spacecraft here, this is NISAR. I think Ora can probably say more about the spacecraft.
Oh yeah, sure. Yeah, so this is a spacecraft that is a partnership between NASA and the Indian Space Agency. And it is what they call a synthetic aperture radar. And that's kind of like science speak, right? It is going to be orbiting Earth, and it is able to look at Earth with radar. And what radar does is it can sometimes see through stuff. So you can make maps of like the seafloor. Or you can do a variety of things. I'm not entirely sure everything that NISAR is going to do, and I don't think they have a clip here for it, but it is an Earth orbiting synthetic aperture radar. Is anybody on the line, any JPLers who are NISAR literate? If not, that's okay too. But
I can't claim to be NISAR literate, but I do work on the project. I actually work on the end where after we collect the data, we do the processing so that we can make useful data products that our scientists can actually use. And so I don't know all the instruments on NISAR and how it works, but I do know that at the end of the day, the data is going to flow through my system. We're going to process it and we're going to put it out at the data archive and give it to the people who will actually do things with it. Now, I think one of the interesting things about these missions lately is that we start thinking about what we call science applications of the data. So when some of my earlier missions, when we're getting the science data, we were just thinking about, oh, the scientists are going to do science on it. They're going to tell us something cool. But when you talk about applications, these are people who are taking the data that you have, feeding it into the work that they do, like about like weather forecasts, about like agricultural forecasts and so on. And so if your instrument is providing data that is directly informing the day-to-day stuff of what's happening in the US government and other places, it's like really important that the data flows and flows smoothly. So that's my input. And there's a little bit there about the NISAR, right?
Yeah, it mentions that it's Earth orbiting and studying Earth's surface, earthquakes, tsunamis, volcanoes. And if you click on this, it should take us, well, maybe it won't. You can go look up NISAR though. So once you highlight that, you see that the spelling for you. Takui, is there anything else in this clean room?
Yeah, let me say a little bit about what a clean room actually is. It is often confused with a room that happens to be clean. You'll see people gowned in special garments. These are very specially made. And the room, this clean room in particular is what's considered ISO 7. ISO stands for International Standards of Operation, International Standards Organization, and they set the standards for the number of particles, for example, you could have, and based on that, what the classification of your clean room is. So what does ISO 7 mean? That means that the maximum number of particles you could have in a 1 cubic foot of air, and that's the maximum of 10,000 particles that are like half a micron. And how much micrometer, and how much is a micrometer? Your hair is roughly about 100 micrometers. So half a micrometer size. But please note that 10,000 is the upper end. Once you reach over 10,000, you're no longer an ISO class 7 clean room. So majority of the time, the clean room is at below 1,000 particles per cubic foot. The floor is a special conductive floor to avoid any electrostatic discharge and therefore frying any electronics on the spacecraft. And the little gray thing that you see with the holes on the floor is for cables that run to the test room, the test complex, which is over to your right, and you can kind of see through the windows. So if you pan towards the right, if you can, right there, yeah, you can see a room there. Often they try to set up testing so that they can hook up everything to the spacecraft, and then the test results can come in the other room, so you don't have a whole bunch of people in the clean room that entire time. That also helps keep the clean room cleaner, because people are the worst thing you can bring to a clean room. Let me not take up too much more space out of high bay 1. So before you bring stuff, before you go into high bay, wait, is there, I should have thought of this. Do you have a picture of high bay Bob anywhere in this picture by any chance?
Let's see, high bay Bob used to be on the floor.
Yeah, he moves around, so we move him.
There he is.
There he is, yeah. Yeah, it's okay. There he is, yeah. So we call him High Bay Bob. It's a mannequin, and often he's the way he's garmented is whatever the standard is at that time for that clean room. At the moment, you're seeing a disconnect between what he's wearing, which is a full bodysuit complement versus what the folks are wearing. I think it's because this happened at a time when that giant white container you see by High Bay Bob was that two different projects were happening at the same time. And the cleaner project with the bodysuit requirement was already packaged up, so it was safe enough that people could switch to the frocks. Okay, so before you bring stuff into the high bay, for example, whether it's high bay 1 or high bay 2, you have to go through the gowning process. So should we go to the gowning room, perhaps? Right, so you go to the gowning room. The door that you see ahead of you is the entrance to the gowning room. The garments that are hanging on the rack are ones that people can wear a few times before they put it in the laundry. They have little tags so everybody can tag their own so they don't end up wearing each other's garments. They gown up in this room, and then they go and go into, oh, there you go, cool. Yeah, so this is just outside the gowning room. You clean your shoes, you put on your shoe covers, your hairnet. Oh, in this case, he's wearing a bunny suit, so. That's an electrostatic discharge wrist strap. So to make sure that they are fully grounded, and the garments they're wearing, and that's an air shower, and you get bombarded with high velocity, cleaner air than the clean room is to release any particles that might be stuck to your garments before you go into the gowning room. Thank you, that was lovely. Okay, and then you're safe to go into the high bay. And if you're moving in or moving out hardware, that's where the airlock comes in. So the gowning room is kind of like an airlock for people. The airlock is an airlock for moving stuff in. And we have large lift equipment for doing any kinds of either repairs or moving stuff. And so this roll-up door that you're looking at right now in front of you is leads to outside. So if you're bringing stuff in, you bring it in to the airlock, you close that door again, you wipe everything down properly per clean room requirements, and then you remove things from their containers, you wipe them down again, and you move to that cleaner side of the room, and look, it says go to clean room 1. Over to the left, oh, okay, yeah, and now we're in clean room 1. Or you can go to high bay 2, which is a slightly different airflow. This one has Psyche in it. The tour is a little bit behind. Right now we have a Europa Clipper in there actually, and I think there's a YouTube website if somebody wants to stick that on the chat. But somebody can talk about the Psyche mission. This is the tallest clean room at JPL. Actually, it's the tallest lab/room, and in the ceiling there are 250 of those specialized filters to help keep the room clean. So this is 70 foot high, and the room is kind of like a cube. It's 70 feet by 70 feet by 70 feet. Cassini was assembled in this high bay, as well as many others. So was SWAT actually.
So let's quick, I think we had some questions in the chat, and I think we had some questions from before. So April, what was that question that we got before about the tape?
There was a question in the Google Doc in high bay 1, I believe there was a lot of tape on the floor, and there was a question about if it serves a special purpose.
Yeah, so that particular tape is very low, what's called very low tack. The adhesive isn't very strong. So if they have to use it to mark something, if the project has to use tape to mark something, they'll use that because it is less likely to leave a residue behind that we cannot clean, because if it leaves a residue behind, it becomes contamination. So they call it flash tape because it is often used in electronics temporarily. You know, if you want to put a little note on something, you would use this tape, and then you easily remove it, and it doesn't leave any of its adhesive behind. So each project has its own requirements about why they put stuff there. And I don't know what that particular project's requirement was, but I do know that they left a little bit more behind than we wanted them to. So my team had to spend many hours cleaning all of those tapes out to make sure that the floor is clean.
There was another question about how do you control or monitor how many particles are in a clean room?
Okay, so it takes very complicated AC systems. They're actually called air handlers. We have particle counters in the room that measure the particle counts every minute and send the data to a database that I monitor. And the software for that database allows me to set up alarms and notifications. So I get a notification if the particle counts are starting to reach the higher levels, so that I can check to see what's going on. And if the room is empty, as nothing is going on, and the particle counts are going up, that suggests something is wrong in the air handler system or the room. But the air handler is very complex. They use many huge motors that can be like 2 tons each, and air is pushed at very high velocity to get through the resistance of those HEPA filters. And by use of particle counts, we'll monitor that. The rooms are also at what's called positive pressure with respect to a neighboring room, so that when you open a door to enter, the clean air rushes out, making it less difficult for the less clean air to make its way in and contaminate the room. The idea is all the air that enters the room has to be filtered and clean. By the way, High Bay 1's entire volume of air gets replaced 6 times per hour. High Bay 2 is more like 10 times per hour, the entire volume of air. So it's very energy, what's the opposite of safe? Uses a lot of, clean rooms tend to be energy hogs. What happens if the particles are trying to be cleaned? No, it depends on what's going on. There are times when we have to do things that we know is going to introduce more particle counts. At those times, we'll actually put protective covers on the most critical hardware. And afterwards, yes, we do cleaning as necessary, and we'll monitor to make sure that the particle counts are back to normal before the mission can continue its work.
Taguya, I have a follow-up question. I remember that there was a station fires a few years back. The air quality at JPL got really bad. So what was the impact on the clean rooms?
So the largest impact on clean rooms was that the particle counts got so high in the air that, at least for staff, at some point, the pre-filters, these are the filters at the front end that don't allow the large particles to get through, they got so loaded that they wouldn't allow any air to get through. And so in response, the motors just started to work harder and harder, and they just kind of, fortunately, rather than burning out, they shut down. So all air just stopped going in, which was fine, because at the time the projects were already standing down and all critical hardware was covered to protect them. And interesting, and actually, because of the positive pressure in the room and the fact that nobody was opening or closing the doors, the particle counts in the rooms, in the clean rooms, stayed quite good. And, you know, once the pre-filters were replaced, everything was fine.
That's cool. Any other questions about the clean room? Because I'm not sure, but I think we may be moving on. So where are we off to next, Oda?
We are off to the Mars Yard.
Ooh.
We have Carrie Bean here to talk to us about the Mars Yard.
Yeah, thanks. So my name's Carrie Bean, and I am the Deputy Lead Rover Planner, aka Mars Rover Driver and Robotic Arm Operator for Curiosity, which has now been on Mars for just over 10 years, which is pretty exciting. And the rover you're looking at there is actually the twin rover for Perseverance. So in contrast to the clean room, where things stay very pristine and clean, the Mars Yard is where we can play around and get dirty with our spacecraft. So we like to build extra models of our spacecraft that we can use to test things here on the ground. So we call them test bed versions of our rovers. And so for Mars rovers, even, we actually build two different versions. So we build one that is as accurate as possible. Usually we can't build duplicates of like our instruments or things like that. So it's really just trying to be as accurate as possible, but maybe not 100%. And over in the other corner there, you can kind of see our Scarecrow rover. And so it got the name Scarecrow from Wizard of Oz if it doesn't have a brain. This one is entirely controlled actually through an iPhone app of all things. And this one weighs here on Earth what it does on Mars. So Mars is about a third of the gravity that we have. So this one weighs about a third of what the real rover would weigh. So the reason we build these two is the one that is as high fidelity as we can make it is to test anything with the robotic arm motion or sample delivery or anything that requires a lot of the components of the rover. Whereas if we're testing over different types of driving terrain, the rover that weighs the same here on Earth as on Mars will give you the same pressure on the ground. So you will slip in a similar way if you were driving up a hill or things like that. So that's why we try and build two different versions of our Mars rovers. So this garage is where we keep them nice and safe. And we can do a lot of testing in here. This is usually where we're playing around with the robotic arm. But if you turn around, you can see a lovely deserty looking area that looks like Mars. And so let's go ahead and hop out there. Yeah, and so for both Perseverance and Curiosity, the real ones are actually nuclear powered. So they have what's called a RTG, or radioisotope thermal generator, which is a chunk of decaying plutonium that generates heat for the rover to keep it warm on Mars. It's not exactly a warm planet, and also to turn into power for the rovers. Well, humans working around nuclear things is typically not a good idea. So instead here, we just plug them into the wall. So you can see the very long cable. We can drive all over the Mars Yard. We just have a very long extension cable. Usually there's at least one person out there just doing cable management as we're driving around the rover. And you can see the rover has been driving up one of the slopes there. So along this edge of the Mars Yard, we actually have different slopes at different angles and also of different materials. So Mars is not a nice flat pancake for us. In fact, Curiosity has been driving up a mountain for several years now. And so with that, we have to test what it's like of what is it like to try and drive the rover up a sandy slope versus a rocky slope? How much kind of slip are we going to get? When I train more Mars rover drivers, I actually make them come out here and drive the rovers around just to get a visual look of, one, they don't move very fast. We're moving at like a meter or about 3 feet per minute. That's about our fastest speed that we can go. And the arm also doesn't move very fast. We want to be very delicate, especially because these arms are very heavy, and also gets them a better feel of like, okay, how much is the rover actually slipping if you're driving up a 15-degree slope? And you can see all sorts of rover tracks on the ground there. And in the distance behind that set of blocks there, you can see giant piles of sand. So that's where we can do our testing of driving over sand dunes. Mars definitely has thrown a lot of sand dunes at us, and they can be very slippery and tricky for the rovers to drive over. So we have this area over here where we can test that as well. And we can put them at whatever angle and size that we need to. And you can look out and see all the different types of rocks. You can see there's like a little trench kind of further in the distance. We can make the Mars yard look however we want it to. Some of these rocks are just kind of fake big rocks. They're actually hollow on the inside. Some of these are actually from scientists who have gone out in the field and said, oh, this rock that I found out in the desert is actually very similar to a rock we found on Mars. And they'll actually bring it back for us to either test with our robotic arm for drilling, whether it's going to be a hard or soft target to drill, what it's like for the rover wheels to drive over. Curiosity had a lot of issues of holes appearing in the wheels. And it turns out that the Mars rocks in Curiosity's landing site were much harder and pointier than we had expected. And the wheels are only about as thick as like a soda aluminum can. And you can imagine taking a soda can and pushing it on a pointy rock, you're going to make a hole pretty quickly. So one of the ways that we adapted that was actually by essentially inventing traction control for our rovers. And so they can differentially change their speed. All of that had to be tested here in the Mars yard, driving over the rocks to see the effects. We love doing all of this testing up here because it's much easier to fix something here on Earth than it is on Mars. So I've actually spent a lot of my summer up in the Mars yard here because Curiosity is about to do a large flight software upgrade. So this is essentially the rover's operating system. And so we want to do a full checkout of every command, every little component of the rover to make sure that we're not finding any bugs before we send it to Mars. It's much easier to fix the code here on Earth and retry it than try and debug it on Mars. So the Mars yard and our testbed rovers are a very critical component of our mission operations at JPL. Yeah.
Do we have some questions about the Mars yard?
Yeah. Not seeing any.
So Carrie, I got a question for you.
Sure.
So I noticed that the dirt, if you will, on the flat part here is kind of reddish and your sand dunes are kind of like whitish. What gives on the color?
Well, that is a good question. I am not quite sure what the Mars yard dirt is made of. But at least on Mars, we see a lot of the reddish color is because it's got a lot of iron, and that's actually rust. And so we've noticed with Curiosity and also with Perseverance, that once you kind of brush off the top layer of dust, the rocks are still very like gray or white instead of the red that you know from Mars. So that may also be what's going on here. Sand tends to be a lot of silica, which is kind of a white to clear material usually mixed with, some other components. So that tends to be why, sandy beaches are kind of that like light tan color for that reason.
So there was a question that popped up. Alice asks, what rover models are currently stationed at the yard?
Yeah, so right now, the building that we have there that we started out in actually used to just have like one, it was wide enough for one rover. But now that we both have a Curiosity and a Perseverance double, we actually had to expand the garage. So it just recently became this much bigger building. And so in there we have the Curiosity Spare, which we call Maggie. And it is an acronym, and I think it's like Mars Automated Gizmo for Engineering or something. I don't quite remember the acronym. I know Gizmo is one of the G's. And then the Perseverance model is called Optimism. Again, that's an acronym, and I definitely don't remember what that one stands for. It's NASA. We love acronyms. We got to come up with fun acronyms. And in the kind of smaller lighter color garage kind of off to the right there, that's usually where Scarecrow is. And also in there, from that wheel testing I mentioned for Curiosity, there's just shreds of wheels in the back of them just being torn apart from driving. So it's kind of fun if you ever get the chance to go up here. Yeah, so I think this was before, I was just gonna say in the room, I think this was before the Curiosity model had been moved back up there because they had to move it to a different building at JPL to get it out of the way while we were expanding the building. So I think this just happened to be before we brought it back up.
So we have another question. What are the main features of the rover that has changed significantly to make the rover more weatherproof?
Yeah, so for the rovers here, we tend to not really change a lot about the rover. We don't have as many of the heaters though, because it's a lot warmer on Earth than we would expect on Mars. And in fact, because it is Southern California, and as you very well know here in Pasadena, it can get quite toasty. We actually have the capability to plug in a specific airflow line to help keep the rover cool. But even then, if it gets above 90 degrees or so, your test may be cut short just because the rover is getting too hot. So that's part of the reason we like having the garage where it's nice and air conditioned inside. So unless we really need to drive a lot, we actually keep the rovers in the garage, and we can do all of our robotic arm testing and everything inside the garage without any heat issues. And so it also made it pretty miserable this summer with it being, in the 90s to 100 each day, having to get there super early in the morning, right as the sunrise is happening to have time to get out there. And the same jackets they wear in the clean room, we have to wear here, because again, we don't want to, fry our rovers from electrostatic discharge. So they're not very breathable jackets. So you're standing outside in like 100-degree weather with this plastic jacket on, and it's not very pleasant, but we get it done.
Okay. So this is more of a NASA question. How do you come up with acronyms? And how do you make sure you don't reuse it?
Oh, we definitely reuse them, which causes confusion in and of itself. And acronyms, it can either be something that just kind of naturally happens, or you are very dedicated to use a certain word and you kind of come up with it. I can give an example. So as a giant Star Wars fan, I really wanted to use PORGs as an acronym because I love the little Star Wars org birds. And so I just so happened to be able to brainstorm with a team one day on how to use it. So it stands for Practical Operational Readiness Gambits. And so they're training exercises for new rover driver team members. So that one I picked the word and I made the acronym later. Sometimes words kind of come together and you're like, oh, that actually works pretty nicely. So it just kind of depends on what you're going for.
I think a friend of mine actually tried to put a proposal for a project and she may have named it Mando.
Yeah, on Curiosity, we have software tools called Vader, R2, 3PO, Skywalker, and I forget which project it is, but there's also one that used Tribble as well. We also have Star Trek fans at JPL, as you can imagine. So there's some good acronyms out there.
I have been in a situation where after a project was selected, the proposal had one name, and NASA strongly encouraged us to change it for copyright infringement issues. It's a branding conflict. So we did.
All right, are we ready to move on from Mars Yard? I think so. All right, so I'm going to head on over to the Microdevices Lab.
I'm done now.
April, what the heck is the Microdevices Lab?
Okay, the Microdevices Lab has been around since 1989, and our mission is we have end-to-end capabilities to support the design, fabrication, and characterization of advanced components and sensors. So essentially what we are is JPL's semiconductor fabrication facility. So because of that, we have a lot of the same capabilities that you might expect to see in an industrial semiconductor fabrication facility. But the difference is we're not making, you know, thousands or millions of the same kind of chip. Our focus is really to make components and sensors that sometimes NASA just needs one of them, or you know, fewer than 10 for a mission. And so we have the capabilities starting from the raw materials, so a blank silicon wafer, to build up the component or the sensor layer by layer. We have all the equipment and facilities needed to do all of the patterning work, all of the deposition work. And sometimes we're looking at devices that have, you know, 20 to 40 individual layers. So if we could go back out into the hallway, I don't know how or if we go to the lithography lab. So it's a yellow, one of those yellow rooms. So some of this may look familiar in terms of the facility. It is also a clean room facility similar to high base 1 and 2 at the spacecraft assembly facility, but the Microdevices Lab, we have about 8,000 square feet of clean room space, and that's ranging from class 10 to class 100. So it's cleaner than a hospital operating room. And this room, for example, class 10 is cleaner than the high bay facilities that Tugui was showing us earlier. And the reason this particular room is yellow, this is where we do all of our patterning work. And if any of you are into the, or are familiar with film photography, this is very similar to a photographic darkroom, where those are red because they're dealing with materials that are sensitive to visible light. Here, the patterning materials we're using are sensitive to ultraviolet light, or sometimes even shorter wavelengths like extreme ultraviolet or X-rays. So we are able to use yellow light because that's outside of the wavelength range that our materials are sensitive to. So we can have our materials out in the room, moving between machines, and not worry about exposing the pattern outside of the machine. As I said, the semiconductor device manufacturer, we're building up the structure layer by layer, and each layer has to be patterned separately. So we'll deposit our pattern. That can be, the layers can be made of metals, they can be insulators, they can be semiconductor materials, and we have the capability to deposit all of those in the lab. We're talking about a very thin film on the orders of microns or sometimes nanometers, and we have the capability to control the deposition rate, you know, sometimes even depositing a single atomic layer at a time. If we can go back out into one of the main rooms, let's go to the, sorry. If we go down the hall, I'm going to focus on the work that I do, which is way at the end of the hall. If we go to the tab on the left, I think we can choose the ultraviolet and Okay, so this is the
Is
machine
that the
that
right one? The UVIR?
Yeah, I actually work on this machine. It's a giant vacuum chamber. And if you pan around to the left, you can see all of the control panels. So here we have 3 electronics racks full of equipment that's all connected to the vacuum chamber that allows me to control all of the equipment that's attached to the vacuum chamber. And you may be able to see where the chair is there at the desk. That's my command center where I have 4 computers that interface with all of this various equipment on the rack in the vacuum chamber. I'm working with silicon-based imaging devices. It's the same kind of device that's in your digital camera or your cell phone. They're like silicon CCDs or CMOS arrays, and that's what allows you to actually take and store pictures. But the process I'm doing changes the way those devices behave so that you can, they're sensitive to ultraviolet light in addition to visible light. So what this system allows me to do, if you scroll back to the right, we can look at it while I talk about it. It's called a molecular beam epitaxy system. And epitaxy is a fancy way of talking about a single crystal. So we're looking at very high purity silicon wafers with sort of a single crystal arrangement of all of the atoms in the active layer. And I can use this machine to deposit very, very thin layers of silicon. And by very thin, I mean I have control at the angstrom level. So we were talking about microns earlier when Takui was talking and how the human hair is about, what did you say, 100 microns or just a few microns in diameter. This is 4 orders of magnitude smaller than that. So I really am able to control where all of the atoms go, and I can grow material so that it looks like a single crystal and there are no grain boundaries. And then I can also control doping. So if you're familiar with semiconductors, or from your high school chemistry, you may have learned about, or maybe not high school chemistry, maybe second year chemistry in college, about doping of semiconductors by using materials from a different row or column on the periodic table to control the amount of charge that goes into the system. We can then change the way the device behaves. So instead of just being sensitive to visible light, we get all the way down into the ultraviolet. So what I wanted to talk about, this is a dedicated tool, but a lot of the tools in the Microdevices Lab are shared. So a lot of people are using our deposition equipment. And yeah, does anyone have any questions?
While people are thinking of questions, April, I've got one for you. Could you talk a little bit about your academic background that brought you to JPL?
Sure. My background is in chemistry. I got a bachelor's degree in chemistry, and then I started at JPL as an intern. Caltech has a summer undergraduate research fellowship program. I didn't go to Caltech as an undergrad, but they do open that program up to students from other universities. So I looked at opportunities and got in touch with the advisor on a project that I was interested in. So I came to JPL as a summer intern, and then that turned into a job offer, which was I was very happy to accept after I earned my degree. I was here for 5 years. I was working on various projects One thing that I really like about working at JPL is that you're not necessarily limited by your degree, but really your experience. I was able to work on chemical sensors. So this was something called JPL's electronic nose. It was monitoring air quality on the International Space Station. I was working on thermoelectric materials. Earlier, Carrie mentioned that the Mars rovers have RTGs, radioisotope thermal generators. So I was working on materials that go into those, actually do the conversion of heat to electricity. And I was working on device characterization for the group that I'm working with now. And then I decided to go back to school, and I got a PhD in chemistry, focusing on interface dynamics, so looking at solid gas interactions. Some people call it condensed matter physics. So I'm a chemist by training, but it lends itself well to the work I'm doing now with materials growth in the lab, being able to understand what's actually happening at the surface of the material I'm trying to deposit on. But I'm not called a chemist at JPL, I'm called an engineer. So I do a lot of material science, a lot of process development, and I also get to do some project management outside of the lab.
So we have a question in the chat, actually, from Tammy. She asked, you mentioned that the machine is sensitive to ultraviolet, but it seems like the lighting in the room is not as yellow as the previous room.
Thank you. I should have mentioned we've moved to a different part of the lab. So here, this is after the entire chip has been built up. So it's completely fabricated, and this is essentially the final step. So once it gets to this point, I don't have to worry about the UV light exposure anymore. Thank you for that question.
I actually have a question about, normally the interns that I meet, they're usually either working in mechanical engineering, system engineering, or like coding. And so do you guys actually get interns in the Microdevices Lab? And if so, what are you looking for?
We do get interns. It depends on really the interests. I've worked with interns who were doing modeling work. So a lot of times before you try a new material in the lab, you'll run a model to see how changing the structure that you deposit could impact device performance or instrument performance. So there's some aspect of that. Some people are really interested in instrument building and trying to see how a particular device can help answer a science question. So they'll be more interested on the post-fabrication characterization of a device, trying to push its limits. So we have interns helping us with that. And just a couple of years ago, my colleague and I were working on building a new piece of equipment. Sometimes we can buy equipment that's ready, essentially plug and play, but sometimes there's nothing available, and so we'll build it in-house. And we hired interns to help design and build and also do programming for the user interface for that instrument, and doing all of the system control the computer, all kinds of things. And then there are also, of course, students working in the clean room, learning how to use all the deposition equipment and all the characterization equipment.
So for your interns, are you looking at undergraduates, graduate students, postdocs?
All levels. I worked with folks at all levels.
Seems cool. So if you guys are interested in this, or you're like in chemistry or physics, you should definitely ask more questions.
I see a question from our pre-submitted questions that April, you might be able to take a stab at. During the chip shortage, did you see an increase in demand at JPL for the chips, or is every semiconductor that we use manufactured within JPL?
Where is this question?
It's in the Google Doc.
Okay, during the chip shortage, we did have experience. So I work on a project where our chips are being integrated with electronics, and so we're designing and building electronics, and often using commercial or flight grade chips, and we definitely saw problems there. We had problems getting raw materials. We had problems from our vendors. Their inventory would be wiped out in a matter of a few hours online. And then we were even impacted. So our clean rooms, gowns, and gloves, we had trouble sourcing those as well. So it's been affecting everybody. But to answer, is every semiconductor always manufactured within JPL? The answer is no. If we can buy it, we will. That's the preferred way to do it. We only want to put our resources into building something that's not commercially available.
Very good.
That's actually a great point. That's one of the things that we talk about at JPL is we're not here to build things so that you can buy it off the shelf. We're here to basically push the cutting edge of technology. And so where we want to put our efforts is in the stuff that no one has done before, and not in the stuff where, it's like we have a lot of experience and we can keep doing what we've been doing. And that's, I think, one of the great things about having interns and having a diverse workforce. You get all these crazy ideas and you're just like, let's try it. So there was a question in the Google Doc that I think that we should just talk about here. And it was, how do you test equipment for space? So April, were you the one that was answering that?
Yes.
Yeah. You wanna tell everyone?
Sure, but I wanted to share my favorite acronym for the projects I work on.
Yeah.
And I work on a project called Fireball. And it stands for Faint Intergalactic Redshifted Emission Balloon. So that took some work to come up with, I think. So yes, how do we test equipment for space? I think this is a great question. I think anyone should chime in, but the first thing we need to do is to figure out what environment we're going to go to. It's the instrument or your chip, what is it going to see? Because the environment in Earth orbit is very different from the environment on Mars, which is very different from the environment that we're going to see on Europa Clipper when we're flying near Jupiter. So we figure out as much as we can about that. So that will include pressure, radiation environment, temperature, all kinds of things. And then we do as much testing as we can. So we have thermal vacuum chambers all over the lab. We can put devices or instruments or sometimes entire spacecraft into vacuum chambers, and we can do thermal cycling in that chamber. We can do testing during the thermal cycling and after to make sure that things are working the way we expect them to. We can expose parts to radiation beams and then do testing after to make sure things are working the way we expect. And I think an important point is that some performance degradation is okay as long as it's understood. And also that we're not testing the actual parts that are going to fly. We're testing things that like the spares or the engineering units, because we don't want to prematurely damage the parts that are actually going to fly.
Could you talk a little bit more about the thermocycling? The reason I'm interested is because for the projects that I've supported, they've involved me in what's known as thermovac testing. And this is where we put our instrument in a thermovac chamber and we try to get it to the right temperatures for us to collect data. And you were saying that it's not that it has to perform perfectly every time, but it's well understood. You've also said something before about characterizing instruments or something like that.
Does anyone else want to take this one? I've mostly been working on R&D. I'm
Yeah.
newer to flight. If there are other folks.
There's also the ETL chamber, the environmental test lab. It's a huge chamber that can simulate space. So often spacecraft, not often, but every time, spacecraft have to go through testing in that chamber, and they can control temperature as well as solar radiation at the right level. So depending on how far the sun is expected to be from the spacecraft, they'll simulate that. And my understanding is they're getting to the point where they can pretty soon simulate not just Martian atmosphere, but maybe even Martian space, including some soils as well. I think that's coming up in a few years. As soon as we have another chamber to use that can be kept clean, then this one can be used for those properties. Let's see, you already said we have chambers of different sizes throughout the lab. They're mostly in ETL though. There's a particular group that specializes in testing temperature and humidity. And then there are shakers. And so spacecraft have to go, or instruments have to go through the shaking that a launch would induce on it. And it has to survive and still continue to work. So sometimes we refer to them as the shake and bake building.
And you also want to, when you're doing these kind of thermal and environmental tests, you want to try to go beyond what you expect your instrument to see, because you expect it to go to 50 C or 50 degrees Celsius, you may test to 60, for example, just to make sure that you've covered all your bases.
Yeah, we often build beyond what's needed because you don't want to be too close to its limit when it's out in space, because you can't go back and repair it afterwards. So it's not like your car where you can take it to the shop if a sensor goes bad. So, yeah.
So I think the most famous example of us building an overbuilding is the Mars exploration rovers. They were originally supposed to work for 90 days, and I think, I don't know if Carrie's back, but was it like 10 and 14, 15 years?
Yeah, so the main reason that they were expected to last 90 days was because the Sojourner rover actually had an instrument on top that measured the dust deposition rate. So Martian atmosphere is very dusty, and so it was measuring how much was falling out of the atmosphere every day and keeping count. And so they extrapolated that information from that instrument and said, based on the size of the solar panels we're sending and based on this rate of deposition, one rover is probably going to last about 83 days and one could maybe last about 93 days. So let's just say 90, it'll be somewhere around there. And that's what they really thought. That's all the data that we had pointing to that. Now, what ended up happening is they went to different parts of Mars from the Sojourner rover, and we have found that that dust deposition rate is different on the different missions in the different locations on Mars. So one, it wasn't falling out of the sky as quickly as they thought. And two, especially where Spirit landed, it was particularly windy. There's a lot of dust devils and wind gusts, and anytime one of those came close to the rover and even hit the rover, it just scrubbed the solar panels clean. So that's the main reason they ended up lasting so long. And of course, the JPL engineers are really good at, if there's a problem, we'll figure out a way to fix it. So by the end, both of our front wheels could no longer steer. So we had to do like tank style turning. We also had the robotic arm could no longer move left or right. So we could only look at rocks here. So we'd have to use the rover to physically turn to look at the different rocks. Yeah, it was a lot of fun. I was one of Opportunity's final engineers and worked on the mission since 2007 through end of mission. So I was on it quite a while to see it all go. So dear to my heart.
Yeah, that is sad, Carrie. So Pioneer and the two Voyagers have also outlived well beyond the years. Voyagers have been out there for 45 years now. Pioneer even longer. I don't know the years. And we can't say anything about Galileo and Cassini because they were both purposely lowered into the, well, Galileo's case, into Jupiter's atmosphere, and Saturn's case into Cassini's case into Saturn's atmosphere, in order to ensure that they don't at some point make impact with any of the icy moons, which could possibly harbor the right conditions for life. And so that was done for planetary protection, to ensure that we didn't contaminate pristine moons that we are going to study. And Europa Clipper is one such case. We're going to go and study Europa more thoroughly than we have until now.
All right, so we have a few other questions in the Google Doc, and a couple of things were about internships. So I'm actually going to pop out to our intern page. If you want to learn about JPL internships, you go to jpl.nasa.gov/edu for education /intern, and you get over to the intern page here, and you can learn about our internships. There's a little video here. And if you want to learn about kind of the general internships, that the video is really good. But to learn about the individuals, go to the apply page, and you can see that we have a whole bunch of different internship programs. And different ones, you might qualify for 1, 2, 3, 4, 5 different programs. And the important thing is to apply to every program that you are qualified for if you're interested in interning at JPL. The year-round internship program is just like it sounds. We do summer, we do fall, we do spring, and the MSP program is just in the summer internships just in the summer. And as you scroll down here, there's a couple of others that I want to highlight. One of them that you might not grab your attention, but we're actually partners with PCC on, is the Student Independent Research Intern Program. This program, when you click on it, it'll tell you more about it, and it lists the colleges that we are partnering with, and Pasadena City College is one of those. So this, a lot of our internships come either with a stipend pay or with course credit, and SIRI, as the Student Independent Research Intern Program, comes with course credit, and you work with a university professor for SIRI. And so you can see you can learn a little bit about each one of our programs. There's another one on here I want to highlight too, NASA Community College Aerospace Scholars. If you're like, I'm interested in this stuff, but I'm not sure I want to devote 10 weeks of my summer or a whole semester to it, check out the Community College Aerospace Scholars. This is, you have to be a high school grad, of course, you have to be in community college, but you are only committing for a couple of weeks of the program. It's part of it is online, and then part of it is in person. So it's kind of a fun program. So that's the gig for internships. Each of our internships, there's also NASA actually at the other NASA centers. So we're one of 10 NASA centers. There are 9 other NASA centers around the nation, and they also have internships. We happen to have like 10 times more than any of the other NASA centers. So there's more opportunities at JPL, but if you are interested in going to one of the other NASA centers, you should apply there as well. And then if you're looking for just a job at JPL, we have JPL jobs, so you can check that out as well. So number of different opportunities. Usually you have to have like a 3.0 GPA, but you don't have to have like straight A's or anything like that. Let's see. Other questions from the Google Doc. I want to pose this to my other fellow JPLers. What made you choose JPL?
I can answer this one. So I'm in robotics, and it's kind of already a semi-niche field. So when I was looking for jobs, I was interested in doing like research-based stuff, but a lot of the areas of robotics that were in the industry were more focused on manufacturing or focused on, specifically autonomous driving, that kind of stuff. And I wanted the opportunity to be able to work on a variety of different projects. So be able to not only do, projects that range from, swimming robots to large computation robots, to drones, to mobile platforms, to arms. But I also wanted to be able to have some level of flexibility to do algorithm development versus maybe more systems level engineering versus, human computer interaction stuff. And so JPL was nice because it kind of sat for me in between industry and academia. So there was an ability to do, more basic research, but also work on problems that are, have an actual application, and there's somewhere for that research to go and to be integrated into. And then it also gave me the opportunity to be able to wear several different types of hats and do a lot of different things to develop my own set of skills.
Cool. Other JPLers want to jump in? What brought you to JPL?
So I'm not sure if I should admit this, but it was actually the distance from my house. I had 2 job offers. One of them was in was it El Segundo, and the other one was like 11 miles from my house. So I picked that one. But what I will tell you is that once you join JPL, meet awesome people here, you get to go around campus and stuff, you fall in love with it. And so you have people who have been at JPL for over 30 years. And, like any workplace, there are things that you might complain about, but there is something that ultimately makes us stay. And one of the things that I like about it is I never fully feel like I've left college. It feels like a very academic and I shouldn't say academic, but kind of like more like a collegial environment where like I might be seeing managers and talking to managers, but I still can kind of talk to them as my peer, talk to people. There's so many interesting people in lab, and you would not know until you actually start having a conversation with them.
Yeah, that's true. And I can, as a person who, JPL is my 3rd NASA center. I worked at 2 other NASA centers before JPL. And I've been at JPL the longest, and it's primarily because I just really like the atmosphere and the work we're doing. Carrie, I see your camera on.
Yeah, I was going to add, I got to spend some time at Johnson Space Center as well in Houston, and it was like just a totally different feel of JPL. Like I'm wearing like a t-shirt and jeans 99% of the time. I've like given presentations in full cosplay costume before, and like people are just like, that's Carrie. Whereas like Johnson Space Center, it's like minimum polo and slacks, very formal. Whereas like JPL, you can just like go talk to anyone and everywhere. JSC was very like strict, like hierarchical. You have to go through this person to talk to this person and that sort of thing. So that's another thing I like about JPL is like, I know like tons of people at this point, and it's so cool like getting to know everyone, and you can just like ask someone for coffee and meet up or anything like that. It's very chill.
Any other JPLers want to chime in on what brought them here?
So I can relate, except that I wanted to work in the space program, or I should say at the time I was thinking aerospace, and most of the companies at the time were doing DoD work, and I wasn't interested in that. So JPL was the one I was interested in, and so I applied there. I started applying while I was an undergrad to see if I could get a part-time job. One time I got an offer, but it wasn't really what I wanted to do. So I passed that one. Lucky for me, I got another offer just like 3 days before I was graduating. So I had my graduation on Saturday and I started JPL on Monday. Didn't have even a break. But once I started at JPL, I fell in love with it. Like you said, I never stopped going to college. Actually, for a while, I was having a hard time finishing up my thesis because I was having more fun on the job. Yeah, and I mean, you just never stop learning if you want to, and you can grow in different careers. I've changed, kind of looking historically. Like I said, I've been at JPL over 36 years. I've definitely worn kind of a very wide 3 different hats so far. So yeah.
Tui, what is your academic background?
I have a master's degree in physics. It was from a local college, and that kind of made it easy for me so that I could concentrate on my work, which was in research. So that was fun. That's what I wanted to do. Experimental research is what I fell in love with as an undergrad in physics, and that's what I wanted to do. So I started out in a science division, doing experimental work. So it was exciting. I was the equivalent of what's sometimes referred to as a lab rat, or, you know, in a nicer way to say like a research assistant. But I worked on my master's degree while I was working at JPL. Yeah, and I ended up doing my thesis on a project that I worked on as a JPLer. I was studying the Antarctic snow and its optical properties in order to prepare for the Galileo project's arrival at the Jovian system. So it was just too much fun.
Cool. And so I'm going to move on to another question, but I'm going to start with you, Takui. What is the hardest part about working at JPL?
You know, the hardest part is, you know, when you are passionate about your work, it's very difficult to force yourself to sometimes just step away, you know, especially if you're not doing the kind of job where you're the only person that can do this for the next 12 hours and you're on shift, for example, right? So that's the hardest part, tuning out. Just that's really difficult to tune out. I've had issues with that, as I've been told by many managers. I go on vacation and answer email, and managers don't like that. So they kind of like it, but they don't like it, right? On the surface, they don't like it because they want to see, they don't want to look like they're pushing their employees to work while they're on vacation. It's inappropriate. But at the same time, it's kind of a relief because then they have to deal with an issue that came up, you know, while I'm away. So, yeah.
Okay, thanks. Anybody else?
Yeah, I can add. I think for me, it's the feeling of imposter syndrome, that like voice in your head that says like, oh, you're not good enough. What are you doing here? So my background is in meteorology. I was a storm chaser. I studied the weather on Mars, and now I am like hardcore engineer roboticist person. So I've had to learn everything on the job in that regard. And, you know, even though I am the deputy lead, I'm still like, what am I doing? Right. So, you know, fighting that voice in your head can take a lot of energy. Luckily, there is an amazing community at JPL. We have our own like Slack channel where we all like lift each other up and support each other. And, you know, if you're feeling bad, you can post in there, and you have like a little cheerleader squad to bring you back up. So that's been one of my favorite things. Facing this hard problem, but you get support. So good part about JPL.
And April, I saw you flip your camera on. Do you want to chime in there?
Sure, I will say yes, imposter syndrome is a big one. Thank you for bringing that up. But something for me that comes to mind, you know, a lot of us, you know, come from, we did research as undergrads or in our master's programs or in our PhD programs. So we come from very academic backgrounds where you want to dig deep into a problem or, you know, something new and figure out what's going on, especially in the Microdevices Lab where we're building new materials and new functionalities, but you don't always have the resources, like the money and the time to dig down, to go back to first principles to solve a problem. So sometimes if something works well enough, great, deliver it, you're done. If it is not working, you know, you have to abandon it or figure out some way to find someone to pay you to solve a problem that maybe they don't really care about as much as you do as an academic. So that can be challenging. It's being told to move on when you really want to dig deep.
Yeah, for sure.
I have an add-on to that.
Okay.
So the hard thing about working at JPL for me now these days is, as I've been at JPL longer, I've got into a lead role. I don't get to do the things that I used to do. Like, I don't get to dig deep into a problem or try to solve it. I actually have to delegate to other people. And part of the problem is like, the stuff that I'm doing now is important. There's a reason I'm in this role, and that's how I should be spending my time. I can't necessarily be spending it doing the things that I used to do like 2 or 3 years ago or when I was first hired. And at the same time, it's challenging to be able to give that task to someone else and let them own it and let them make their own mistakes and just be happy that somebody is taking care of the problem. And so this kind of goes into, there are certain problems I can't even say, oh, I should have this person on my team do it because they're already busy. And this is where I'm like, hey, interns, if I can bring on interns, you know, it's a good for their education. I can have one person whose only job it is to worry about that one problem. And if they are able to come up with a solution, that's fantastic. If they're not able to come up with a solution, at least they have made a little bit more progress documenting it, exploring the space, and letting me know like what was a good idea, what was a bad idea. And so that's why I am so happy to bring interns on board.
Well, and speaking of interns, I know like several of us have had interns. Can some of you speak to what do you look for in interns?
I'm just letting other people talk.
I guess for me, a lot of the projects that we work on are C++ based. So I do a lot of software. And so not everyone is usually familiar with C++, but certainly harder to come into a internship and start a project that's thousands and tens of thousands of lines of code that are all C++, having not experienced either like C++ or some type of Java experience. So I know C++ for us is a huge added bonus, or ROS experience. A lot of the R&D robotics projects use ROS, and just another skill that kind of helps get acclimated to maybe the code base or code stack you're working in, or just be able to contribute to the project kind of more quickly.
For me, I would usually look for someone who has some hands-on lab experience. It's not a hard requirement. If I'm looking at a resume, I don't necessarily look at grades, for example. I would rather see some experience with a lab or taking ownership of a small part of a project, even if it's in a undergraduate research lab. That would hold more sway for me than in a physics course.
And I have to add the reason that you hear folks asking for like practical experience and actual skills is that if you intern at JPL, you're given a real job. It's not like some project that we just make up for you, like, do this thing, it's random. No. If you intern with us, you are contributing to the work of the laboratory. Basically, we have a researcher, an engineer who is in need of some additional assistance, and they have a task and they think you could do it, and you're gonna get that task. So that's why we look for real skills.
Sometimes there is a problem to be solved, and the intern will be given the problem and have them come up with their possible creative solution that you can't spell out for them because you haven't had the time to solve the problem yourself. Not that you can think about it, but you haven't had a chance to work on the problem at hand. So yeah, there are specific projects, specific problems that need solutions. And right, at JPL, we don't have interns come in and do something meaningless or just so they can sign off on it. They contribute to the mission.
Yeah, and Paige, if I could can I put Paige on the spot here for a second?
Yeah, sure.
Paige, you came in as a co-op. Could you talk a little bit about like what you did when you were as a co-op? Paige is still with us.
Yeah, absolutely. Sorry, I'm in a general workspace, so I can't really turn my camera on. But I was a co-op twice for JPL. I work in 352, so I'm a mechanical engineer, but in both cases, I was able to work on the Mars sample return project for the lander and then for the capture, containment, and return system, which was really exciting. And I have to say that whole idea of co-ops and interns get real work is absolutely true. I had the privilege of being able to co-op during 2020 and 21, so during the pandemic. And at the time, because of staffing problems, because of 2020, we had to pull a lot of people to make sure that it could launch on time, which was absolutely the right choice. But there was a particular project that definitely probably should have been worked on by full-time engineers, but they said, hey, we have a handful of interns and they're already paid for, so let's see what they can come up with. Long story short, the solution to the problem that we came up with ended up being the one that they ended up choosing for this design, which was really, really exciting to see something that I made as an intern that's going to go into space one day, which is really cool.
Cool, thank you. Carrie, you were going to chime in?
Yeah, I was going to say it may also be the things that you didn't learn in a classroom, the more hands-on experience that applies. So most of the time I've gotten interns, it's actually not been like a coding job or anything like that. So one of the interns I had, for a while, I was the training lead for Mars 2020. So I was supposed to train everyone on how to do their operations jobs for when Perseverance landed on Mars. And I wanted to generate like a classroom structure and have classes. And so I hired an intern who had a background in science. She had like a geology degree and was working on an engineering degree and had experience like leading classroom style education for her club at the school. So that was a great skill set to bring all together to help make these classes. And then I had an intern over the past year who actually was a master's student in library science at UCLA. So our documentation for rover driving was in this very old wiki system that was super broken and out of date. And with her skill set, she was able to completely migrate us to a modern wiki system and organize the information and made a huge improvement in our accessibility of finding information. So it's really cool to like bring in other students, not necessarily in the traditional like, yes, they have an aerospace engineering or computer science degree to be able to contribute as well.
Cool. All right, so we have one other question that is kind of for everyone here. What is the most memorable room or area at JPL and why?
I'll go first, I guess. For me, it is definitely our spaceflight operations facility or our kind of mission control looking building. I forget which of the other speakers mentioned it earlier, but sometimes it is hard to like get away and not be so involved and get really stressed about it. And so if I'm having one of those days where I am just staring at like an inbox of 1,000 emails and just totally like, oh, this is awful, I like go away and I go to the operations facility in the viewing gallery. There's like a nice little room off to the side where you can hide. And I just sit there and I watch the data come back from all over our universe. All of the mission, all of the data comes through that room of looking at Mars, looking at Jupiter, beyond. And it's just kind of refreshing and you can step back and be like, oh yeah, that's why I'm here. Like I get to look at all this cool stuff, I'm helping contribute to getting this science. So yeah, that room right there, that's my favorite room.
Yeah, when you brought this question up, I was typing an answer to it in the Google Doc, and that's exactly what I was saying.
Yeah, and that screen actually up there where you see all the little antennas and all the little squiggly lines. Yeah, so that actually is a public website, so you can actually look in real time at what data is coming from what spacecraft. So this is a live look. And so I like to have this up too, just to watch like, oh, there's the commands that I wrote to drive the rover, now going up to the rover, and I'll find out in a couple hours how it went. And so it's pretty fun to look at the site too.
And the room is always that color. It's always kind of dark, very quiet.
Yeah, I think it's known as the dark room. So I don't know that we have a virtual tour image of this one. My favorite thing about JPL is that pulse LED sculpture in 180. Building 180, the education office building.
Yeah, we don't have it on the virtual tour yet.
Oh, that's a shame. But the reason why I love it is because that sculpture is right in front of the double sliding doors. That is the entrance to the building 180. That's our tallest building. That's actually where our executive council sits. And so my building is opposite of that. And when I'm here at JPL late at night and I'm leaving for the night and I go through, I see a shower of light going down that pulse sculpture. And it just makes me feel good because the pulse sculpture is actually a representation of that DSN data. So it is an artistic, practical representation of data coming down and our data flowing up through the deep space network. and it's beautiful and it's functional, and it really makes you kind of understand, like when Voyager data comes in, it comes in like this one little pulse that just comes down. But when data, like say from Mars comes down, it comes down like this rain shower. It's really cool.
All right, anybody else want to chip in their favorite JPL spot?
My favorite is probably Building 107, which is it's a robotics building, but it's like a kind of very true lab space. And it's just fun to kind of walk around and see all the different projects that are going on, because, you know, sometimes you're stuck in your own work and you forget that there's all these, you know, variety of different technologies that people are working on. So it's really fun to be able to like just see what other people are doing and see some of the progress that they make. You know, if I go every couple of months, like sometimes the robots look different or sometimes they're running, and it's definitely fun to be able to see what your peers and coworkers are working on, and all their hard work on maybe projects that you're not specifically assigned to at the time.
Yeah, I really like the high bays, the clean rooms that Takui was showing us, because you get to see what's being built, like what's going to space next. And like Takui mentioned, that the Europa Clipper is in one of the clean rooms right now, and there's a webcam that you can watch it being built. And a couple times a week we have live streams on YouTube where JPLers will come on and answer questions about that particular spacecraft, that's kind of a fun thing. Okay, yeah, thanks, Glenn, for posting that video. And one other thing that that was asked in the pre-submitted questions was, are there other ways to get involved? So we don't have like a volunteer program or anything at JPL, but we do have a cadre of people called the Solar System Ambassadors, and anyone can apply to be a Solar System Ambassador. You just missed the application period. It's in September. So I put the link in there. Yeah, the Solar System Ambassadors are folks who want to talk to the public about NASA and JPL research, but maybe they might be technical people, they might not, but we prepare those folks with all of the information they need. We have all kinds of telecons, webinars, and get you up to speed on what you need to know to go out and talk to the public about interesting things that we're doing. So that's another thing you can do to get involved. And then there was a question about the first woman scientist hired at JPL, and I had to actually go ask the JPL historians to confirm. And the first woman who was hired at JPL in a science technical role, her name was Barbara, she went by Barbie Canwright, and that was in, I should make you all guess, right? It was 1939. And this Barbie was hired as, we call them human computers. And they were people who either had a degree in mathematics or were working toward a degree in mathematics or had some sort of technical training. And Barbie was a mathematician, and she was hired to compute, to work with the data that came off of some of our first rocket testing. Because we started out as a rocket testing facility. Before we were a JPL, we were just a Caltech research facility in the mountains away from all the houses. Of course, there's houses built up around us now. But yeah, there's a lot of interesting history from that time period. And I see the Isabel, your note in the chat about Rise of the Rocket Girls. Yeah, that's a really good book about our early human computers. So, all right, and yes, to see the link to the Europa Clipper camera. Thank you very much. And yeah, we're coming up close to the end of our tour here. Does anybody have questions? Oh, I see one in the chat. What's the most memorable things you've shared with your interns? Let's see, Carrie's had interns, Land's had interns.
Yeah, I can start. For me, for the most recent one who helped us with our rover planner documentation and helped us organize our rover driver information, we had her on shift and she got to help pick out the drive path for the day. So she got to help guide where the Mars rover was going to go for the day. And that's a pretty common thing for interns who work on the rovers. So I know that we had another one who was working on our engineering cameras, updating a lot of our tools from Python 2 to Python 3. And so her reward was she got to sit in on our planning day one day and actually type in some of the numbers and the commands. So she got to take pictures on Mars. So that's definitely some of the experiences you could have, especially if you work on some of the rovers.
I work with some interns occasionally. I help place some of the interns, and one year, one of my interns got in. This was many years ago. Got in with a group that was working on this crazy idea to fly a helicopter on Mars. Just completely wild. And at that point, this was not funded. There was no funding for it. This was just some engineers at JPL in a lab, like kind of trying to squeeze this crazy idea into their regular work and work on it. Well, you've got a full day's work over here to do on your regular paid job, and you're trying to squeeze in this extra stuff on the side. You really don't have time to work on these crazy ideas fully. And I think somebody mentioned that earlier, that sometimes, you know, we have more work than we can explore entirely ourselves. And so they brought in my intern and said, hey kid, look, we have this idea, and we've got the rover, and then we want it to be able to communicate with this helicopter, and we haven't figured out how to do it wirelessly yet. So figure it out. And they were so busy, they didn't really have a lot of time to help him. And he was just like, okay, I'll figure this out. And strangely enough, by the end of his internship, he had figured it out. And then, of course, you guys know the rest of the story. The helicopter ends up flying on Mars, and it's a wonderful success. So yeah, you get to do some pretty interesting stuff. Any other questions? All right, I'm not seeing any more questions, so I want to just thank you all for joining us today and asking us really good questions so that we could share our excitement and enthusiasm for the work that we do at JPL with you. There are all kinds of jobs at JPL, like you've heard from a bunch of us who have all these, you know, fancy advanced degrees, but we also have jobs for people in the trades. If you are like, I don't want to go to four-year college, I want to just get a job and get working. If you've got some trade school, if you're an electrician, all sorts of things like that. I mean, obviously you saw in the clean room, there's like wires everywhere, right? It's like, we got people who are running those wires. So there's all kinds of really cool technical jobs at JPL. The machine shop, where Tagoy was talking about, you know, machining these different parts. These are folks who have expertise with CNC machines, and maybe they've got a four-year degree, maybe they don't. Maybe they went through an apprenticeship. So there's lots of different ways to get to JPL if it's something you are interested in. We have the business team, of course, too, because there's, you know, somebody's got to run the business side of JPL, all of the contracts, all the finance, all that stuff, so that the rest of us can be doing all the technical work. There's support staff. Some probably one of the most important people in the education office is our support staff that just handles and for every bit of paperwork that we have, and just helps us keep everything in working order. So there's lots and lots of jobs. So considering applying with us.
Yeah, I also like pointing out that we have an art studio at JPL as well. So we even have artists on staff as well. So even if you are definitely not in that technical mind, there's still plenty of opportunities.
Yeah, for sure.
I have worked with interns like in the Microdevices Lab. We have displays in the lower level, and we worked with students to get those updated. So it involves photography, layout, design, all that stuff.
Yeah, good point. When you see a lot of our videos and stuff, you see a lot of really cool animations. You see a lot of our like backgrounds and stuff have really high quality graphics. All that stuff is done in-house. So we have graphics. We have a whole graphics department. We have a video animations department. So just all kinds of stuff. So neat place to work.
We have professional photographers.
Yes. Yes, because we have to document everything we do. Absolutely everything we do is documented.
Yeah, particularly with hardware.
Yeah. Yeah.
Actually, I kind of remember in the clean room, I think when they were doing Mars helicopter and they were mounting Mars helicopter to the belly of the rover just to, I think, show that it would work. There was someone with I feel like it's almost like a TV camera there, and then also with a smaller camera and just documenting stuff. When you're dealing with hardware, there's only so much that people can write down and remember. So they'll sometimes look at pictures or videos just so that they can say, hey, we did put that thing back there, right? That wire was there. It was okay, right? So you go look back at the photos and videos, I guess.
Yeah, especially important in troubleshooting maybe a mission that's out in space already, and you can't go look at it yourself. So looking back at the documentation is important. Or also sometimes a mission's lasting a long time and you get to repurpose it for something else. And you need to look at how things were assembled, how things were connected, and see if you can put your written documentation and the photo documentation together and decide if you can use it for a new purpose. So, all right. Well, thank you again for your time. Really appreciate it. We're going to say goodbye at this point and hope to see you around JPL sometime. Have a good afternoon.
Thank you. Bye.